I need to create another. Okay, let's start now. So we are going to study binary search tree. Binary search tree is a special kind of tree, which basically has got, it's a binary tree. Means, what is the meaning of binary? That it will have two children. Every node or every, you have a node, let's say 5. It can have at most 2 children. It cannot have more than 2 children. It can have 2 or less children, 2, 0 or 1. So let's say it has a child. So I'm writing here, this is the node and this is the value saved on that node. And here on this node, the value saved is, let's say 2. And here on this node, the value saved is maybe 6. So this is a tree. It's a binary tree, which means it can have less than equal to 2 children. Means every node has. And what is the meaning of search? The BST means search tree, binary search tree. So the word search is used because this tree is very efficient for search. Why? Because it follows a property, let's call it as Bst invariant, a kind of invariant property, or a property which means that one property is that always the left subtree has smaller elements. Smaller values, you can say. So take any node, its left subtree will have all the values that are smaller than this node. And the right subtree has larger values than the node. So all the values in the left subtree are small and the right subtree, they are large. So this means there is an ordering in this. Let's consider this. Is it a binary subtree, a binary search tree? Yes or no?
Yes.
Okay. Yes, because it follows that property. There are no left or right subtrees, so you can assume it is following the property. Now let's see this. Is this a binary search tree?
Yes, sir.
Yes, because it follows that property that at this node, if I see, look at the right children, they all have values larger than this. So it follows the property. What about this? Yes?
Yes, sir. Yes, sir.
What about this?
Yes, sir.
Okay.
Sir,
Yes?
sir, since for binary search for a binary tree, every parent should have two roots. So how we can call it binary? Like 7 has only one root,
Okay.
children root.
What about this?
This is okay.
Yeah. So anyways, here 5 had 2 children, so it is binary. Okay. What about this?
Not a binary.
Yeah, it is not a BST because it does not follow that BST invariant. So this is a mistake. This cannot be there. Now it is BST. So in this way, you have binary search tree, which has this BST invariant property. Now,
Sir,
yeah.
sir, if we get two equal numbers, like in this case, we
Okay.
have 2, 7, then
Good question. What about equal nodes or equal values on different nodes? So the answer is generally we don't allow same value to appear in the tree again. But in case you are allowing it, so then your definition will change. So you will say here, the left subtree has smaller or equal values and right subtree has larger or equal values. Basically, you have to add those conditions and you can create another tree of that kind. But in general, we don't allow same values to appear on two different nodes.
Sir,
Yeah.
this left tree has less value. So is it with respect to only the right child or the ancestors also?
See, you look at this node, then in the right subtree, all the values should be larger than this value.
Okay.
And if you look at this node, then in the left subtree, all the values are smaller than this value. Now, how do these two compare? So here the relation will be the original one, that this node has smaller value than all these values.
Okay.
Yeah,
Okay,
that
okay.
relation will hold. That's it.
Okay.
Okay, so this is a binary search tree, BST. Okay, let me expand it a bit. Okay, now let's do a traversal on this binary search tree. Let's do a in order traversal. Let's do an in order traversal. Yeah. How will it look like, the in order traversal? Yes. What is in order traversal? You will do in order means?
In order of 3, then 5, then in order of 7.
Yeah, basically you do in order of left subtree. Then you do in order of the node itself. Let's say it is printing the values. So print the node value. And then the in order of right subtree. That's the algorithm, right? Now let's do it. So in order of, so we are here now. You have to do in order of the left subtree. Okay. So you put this on the stack. Let's say line numbers are 1, 2, 3 line numbers in the code. Now you have a stack. Then you are putting 5, comma, you are on the first line, right? So this node number 5, and you're on the first line. You put it on the stack, and then I'm drawing the stack downwards. So you are here now. And now here again, you have to do the left subtree. So again, leave this on the stack, go inside this statement, 3, 1. You're inside this statement. Now here again, you go to the left subtree. So then leave this on the stack, and you are in this. Now here, left subtree is none. So you don't have to, this statement is done basically. Then you will do print value. Okay, let's print the value 0. then write subtree, which is again none. So this is over. So this execution of this code is over. Now let's pick up the earlier code from our stack. So this is the code. So we are back here. So let's remove this from the stack. So our cursor is here now. Now here I have to do line number 2 now. Line number 1 is over. Line number 2 is print value. So okay, let's print the value 1 and then write subtree. I have to go here. So I leave 1 again on the stack with the line number. We are doing line number 3 currently. So I leave this on the stack and go to this node. Again, this node, I'll print 2. Then this is over. I will go back to this code. So I will take this off from the stack. I'm at 1 now. Line number 3. Line number 3 is done. So this code is also over. Okay, this is done. Let's pick the next code from the stack. So I'm at 3 node and line number 1 is over. So I'm at line number 2 now. So line number 2 is print the value. Okay, I print the value 3. Now I have to go to the right subtree. There is no right subtree. So this code is over. Let's see if there is something else left on the stack. Oh yes, there is something on the stack. 5, 0, 5, 1. I'm here now. Let's take this off from the stack. So I'm here now. And the second line, print the value. In this way, I will continue in this way. So what I will get here is 6, 7, 8, 10, 12. Do you notice something here?
Sorted. The values are sorted.
Yeah, this is a sorted list. So this is a sorted list. That's what we got. So basically, if we do an in-order traversal of binary search tree, it will give us a sorted list, or it will be ordered, basically sorted in the ascending order. So that's what is the message. In-order traversal will be or sorted, ordered or sorted. So that's the thing. Now, what is the advantage of BST? What advantage can you think of in a BST?
Searching is of the complexity big of login.
Yes, very good. So the advantage is that the search is so similarly, actually not just search, but also insertion, deletion, everything, insertion of new nodes, deletion of the old nodes, everything is very fast and of the order log n.
Sir, how is this log n?
How is it log n? Okay, log to the base 2. And so, okay, this is because, okay, now this is a good question. How is it log n? This is true for a tree which has got kind of equal number of left and right nodes, or the size of left subtree and right subtree are almost same, right? If we have 5 here, and here I have 4, here I have 6, then it is fast. But let's say if I have a tree like this, 1, 2, 3, 4. Is this a BST?
Yes, sir.
Yes, it is a BST, but it is highly imbalanced. Therefore, in this case, the search is not log n, but the search is of order n only for such an imbalanced BST. But if we make a balanced BST, which means my left, like let's say if I convert this tree, this BST into a balanced BST, it will be something like this. We have, let's say, start from 2, 1 here, 3 here, 4 here. Or you can also make it like this. You can make 4 here and 3 here. that's also a valid BST. So this is what is a balanced BST, sort of balanced BST. So here the speed up will be there. Okay, that's the thing. So BST gives us speed up when it is balanced. Okay, now let's look at the BST in slightly more detail. Basically, we will add some operations in BST now. You define a BST, you will define the root node, right? The root node is something which you will be having in your class. Let's say you make a class called BST. Here in the init function, you have to keep the variables, right? So the variable will be root only. Some node, some value. It could be none also, but let's give it some value, some node. So basically a BST will have a root node, and then using different operations, you can basically the root node, the node itself will be a class, which will have functions like, or basically it will have variables only, not functions. Here self is there, I'm not writing it. So it's self dot value, self dot left, self dot right. This is a node for a binary tree, basically. And now you, in your this entire tree, you have a pointer or you have a handle on the root node, and now you have to use these variables to access the other nodes of the tree. Okay, so this is how a BST is defined. Now one important function in this BST is to add the values, right? How do you add or insert the values? Define insert a value. And I'm saying the value, let's say in our examples, it is not repeated, which means our value will be always the same. One value can occur only once in the entire tree. There cannot be repetitions in the tree. This is how I'm defining my tree. Now, how do you insert a value? So there has to be an efficient algorithm, and the algorithm is a very standard one. It is something like this. So the algorithm says, you start from the root node. Let's say I have this existing tree, this existing BST. I want to insert a new value. Tell a new number. Tell a number on this.
5.
5. Okay. Insert 5. So the algorithm is like this. Start from the root. That you have to do anyways, because the root is the only thing which is accessible here right now. Start from root. Now what you do the comparison. Compare your value, or let's say the element which you are. Compare this value with the current node. Is it larger or smaller? It's larger. So if the current value is larger than, okay, let me say current node. If value is larger than current node, then insert in right subtree. And if the value is less than current node, then insert in the left subtree. And if the value is same, basically don't do anything, just return. Oh, okay, it should be current node dot value, right? If they are same exactly, then just return. Don't do anything. Means we are not allowing same values to be inserted. Now this is a recursive form, right? And what are we missing in this recursive form? What if there is no right subtree or no left subtree, or the current node itself, you reach the leaf basically, or the bottom? Then what will you do? You will say, if my current node is a dot value, or current node is none, my current node is none, then create a new node. Right? So basically, you start from here and compare our new value, which is 5, compare it with the current node. If it is larger, then good, then insert it in the right subtree. So the same recursion will follow. You will go to this here and insert it here. Now you are here and you want to insert here. So compare it with this node. It is larger. So go to the right subtree and insert it there. Now I come to the right subtree, it points to none. So what happens if this is node? So here is where we will create the new node. So here we will create the new node. Right? I will insert it here. That's the algorithm. It's very efficient because it will have to traverse. No, it will not have to compare with all the values, but it will do only log n comparison with log n values only, right? If the tree is balanced, and that's why we wrote here on average. On an average, it is log n.
Sir, can we insert fractional values?
Yes, why not? Yeah, you can insert fractional values. Let's say you insert 3.5, it will be here. Basically, you just need a notion of comparison. You can even insert strings here, just like in a dictionary. You can insert the strings. If you have the notion of comparison, just like in dictionary, you have a notion of comparison. Given any two elements, you can always find a comparison between the two, larger or smaller, right? So you can also make a binary search tree using that. Okay, is this clear?
Yes, sir.
Yes, sir.
Sir, while performing such operations, how do we ensure that the tree is balanced?
Yeah, that's a good question. That's a good question. How do we ensure that the tree is balanced? The answer is balancing the tree itself is a problem. Means you have to run a separate function to balance the tree, because this tree, the form of this tree will depend on the order in which you are adding the values. Let's say, let's write some values. I will say insert. We start from a blank tree, or let's say I create a new tree, Bst 5. Let's say Bst 1. Insert 2, then insert 3, then insert 4. This is the order in which I'm giving these numbers. So first Bst 1 is created, then I will insert 2. So it will compare with the current value. It is larger, so go to the right one. It's none, so create one here. 2, 3, 4, right? But if I insert in another order, let's say I will do the same thing, but if I do, I exchange the order. I make it 3 first and then 2. Then what will happen? It will make 1. Then it will insert 3. Okay, so where will it insert 3? It will insert it here. Now it has to insert 2. So what will it do? It will go to first here, right? This is larger than 1, so goes here. And it's smaller than 3, it should go here. And there is no nodes, just create a new node. 2. And then 4. It starts from here, goes to the right one. From here again goes to the right one. 4. This is what you get. So basically the tree depends on the order in which you are inserting elements. So you have to write a separate another function to balance the tree. Let's say self.balance something, which will balance the tree. It will say, okay, let me make it like this: 2, 1, 3, 4. This is a balanced version. Okay.
Sir,
Yeah.
if you delete a node, then will the entire structure of the tree change, or a subtree?
Good question. If we delete a node, let's say if I delete this node, how do I remove a node while maintaining the BST invariant? Right?
Right.
Yeah. So we will see that in today's class. How do we remove a node or remove a value while still maintaining the BST invariant property? Okay. So that's it. Now, this was about insertion. And now, since you know insertion, search is also very similar, right? If I ask you to search for an element, how will you search? Look at this algorithm. Search will be very similar, right?
Yes, sir.
So if your value is larger than the current node, then you go to the right subtree and search in the right subtree. If your value is smaller than the current node, then go to the left subtree and search there. And if you found the current node is equal to the value, then you return that current node. And if, okay, the other case is, okay, if none of these, basically you never found, or you reached the none, then just return, right? Return that you couldn't find anything. Okay. So that's the search algorithm. So search is very similar. So let me write down the search algorithm. The search operation. So start from root. And then if my current node is none, then means basically return nothing, which means my element is not there. Return a failure. Right? You can't return anything, and or return none, whatever you want to. Means you make a convention. If current node dot value is equal to the value which you have passed, then you say, okay, you found it. So return value or return current node. Okay. So this is a success. You found it. And if then the same thing, if current node dot value is less than the value, then what do? If your current value is smaller than the value which you are searching for, search in which subtree, left or right?
So left.
So my current value is small, and the value which I'm searching is 5. This is large. So what will I do?
Right subtree, right?
Right.
Yeah, I will go to the right subtree. Search in right subtree. And same way, if the current value is greater than the value, then search in the left subtree. That's the algorithm. Should we stop here for a moment and look at the code? We'll go to a Jupyter notebook and do some coding there.
Yes, sir.
Okay, great. Let me share a new Jupyter notebook with you. Sharing. Okay. So first, let's define what do we define first? Title. Okay. I will call it as BST. So what do we define first? Node. Yes, good. So let's define the node. Class node and define init. So what are the things? Self dot value. Self dot. I need a left child, which I initialize with none for at the moment. Self dot right child, which again I initialize as none only. Okay, this is my node. Now using this node, I have to create a binary search tree. So let's make a class called BST. Inside this class, what should I define? Yes.
Root node.
Root node, yes. It will contain contain a root node. And how do I initialize my root node?
Node value.
Good. That's it. So this is my BST. Yeah, basically, this is my BST. Now, when I write my algorithms, I have to write them in a way that the Bst invariant is always maintained. Okay, let's write the first thing which I would like to do with the tree, insert, right? Because I need to insert the values. Define insert self comma value. I want to insert a new value here. What do I do? So remember the algorithm you had. Algorithm said
First define current node as the root node.
Node equals self dot
so. Pardon?
first like node equals self dot root, and then we will do the comparison node dot.
Yeah. See now, as you saw here, that this insertion operation is a recursive operation, right? It's a recursive operation. So when you are doing the recursive operation, you have to be careful that you don't say my current node equal to root, because if you do that, then you cannot run the recursive thing, right? If I say current node equal to self dot root, then I can't call this recursively, right? So what I do is I will create another function which is recursive in nature. There are, I think, 2 ways to do it. Okay. Basically, one way is that I will write here current node value comma current node, and if current node is not given anything, I will just assume root, and if node is given, then yes, I start from that. This is one way to do it. Another way to do it is that I define this function, and here I define a new function called as underscore insert. So whenever I use underscore, this is a convention that this function I don't use from outside the class. I use it only inside the class. Means if I have to, let's say, define this insert, here I will say self dot underscore insert, but underscore insert, and I won't generally call such function from outside the class. And this is just a convention. So I will say I want to insert at the current node. Basically, I will compare with the current node, right? So I need to compare with the current node. So I have to pass the current node also into my function. So let's say self dot underscore insert. What should I write here? Value comma self dot root. Right. So let's write the insert thing now. Now I know the value, I know the current node. So what is the first step I should do? Let me see if I can do something like this. Just a minute. I'm trying to copy my algorithm here. I don't know if I can do it. Okay. Oh, I can do it. Oh, great. So this is my algorithm, which we just now wrote in our notebook. It's too big, but okay. So start from the root node. That's what we did. We start from the root node, and inside this recursive function, I will start from a current node. Now what do I do? If my value is larger than current node, then insert this value in the right subtree. So what does that mean? Here, if value is larger than current node dot value, then do insert on the insert this value on the right subtree, which means current node dot right child, right? And then if my value is less than the current node, if my value is less than the current node dot value, then I will do the same recursive operation on the left subtree. Okay. Now if my value is equal to the current node dot value, I can say here else if they are same, then what do I do? Oh, did I copy? Oh, okay. If they are same, then I'm not inserting anything. I'm just return. And if now the terminating condition, if my current node is none, the terminating condition should go to the top, right? If my current node is none, then I have to current node equal to, I create a new node like this. Will this work? Let's see. Okay, here is a catch. How do I print the values? printing the values is not easy here, right? How will I print my values? How will I know what is my current tree? So I will use a trick. I want to use a function which can print the tree for me. So instead of using this node, I will be using from binary tree. There is a library called binary tree in Python. I will import node from there. See, I'm not using the binary tree function or the binary tree class. I am just using this class node, which is exactly same as this, but it has got a function called print function, which can print the tree for me. I will just show you. So I will create here print, which will basically do so let's create a new one. Let me call it as, did I run it? BST is a new binary search tree, and I initialize it with the value 2, let us say, and I say, okay, this function is overloaded. I call it as pprint.
So what is the meaning of function is overloaded?
Overloaded means you rewrite a function with something else. It's not working for me. Why is it not working? Pardon? Somebody is saying something?
While calling the function, will just pprint work, or should it be bst dot print?
It should work. Let me stop my kernel. Maybe it is using the previous value of node class. It should work. Strange. Kernel, restart and clear output. Oops. Should be bst.print. Right? Yes, now it is printing. Actually, this will also work now. This should, yes, it is working. bst.print, it's not the simple print. Here, this is simple print, but then this also goes to this function, self.root, which is from here. So it will print this. Okay, let's insert something. bst.insert.
Sir, print is a reserved word, right? So how are we using it as a function here? Print.
Because it's inside this class, no? So I can say bst.print.
Okay.
It's inside this class. Yeah, but you're right that it's generally it is good to define it in with some other word, and that makes life simpler. What happened? Okay, I've not put a value here. Let's put 1. Oh, it's not inserting. It's not inserting. It should have inserted 1. It's not working. Why is it not working? It's not working because here is the problem. When I say current node is none, then I'm creating a new node and I'm assigning this variable to that node, but that does not necessarily link the parent with this node, right? That is the problem. So what I will do is I will take the current node I will compare it. So okay, the algorithm is this, but the problem here is here. Problem is here. When the current node is none, you have to create a new node and link it with the parent, and the parent is nowhere in the scene. That's why you have to do this operation at the parent. So you will say, don't say my current node is none, but say if my value is larger than current node dot value, then you check if your child is present or not, right? This terminating condition should be put on the child. Let me do that. If my value is larger than current node dot value, then you check if current node dot right is none, then you create a node here. Node value, right? Or else you go to the right node and then you compare there. And similarly at the left node, if current node dot left is none, then you create a leaf there. Yeah. So see, the problem with the earlier algorithm was it was just assigning the current node as the new node, right? But that does not link my parent with this node. Now this should work. See, it creates the nodes. And I can keep inserting in any order. 3, 5, 4, -1, 0. That's how it becomes. Right? This is the tree. Okay. So my insert function is working. Let's look at some other interesting functions now. What was the other function we used? Search function, right? We have the search function. Where is it? Let me copy it and give it to you. Let's create a oh, it didn't come. Where did it go? Oh, it disappeared. Okay, let me take the screenshot again. Didn't come. Why is it not? Not coming. I don't know why. Okay, now it will come. Sorry, I didn't convert it into a markdown box. Yeah, now it has come. So now let's define the search operation. Oh, I've defined it there only. Okay. So define search operation. Define search self comma value. I have to search for a value. What do I do? Start from the root. The current node is none, then return. Okay. So what I will be doing here is if my current node, well, again, I have to define it in the same way that I will define self dot underscore search what is it called? Self dot root or value comma self dot root. And here I will define underscore search as like the same way. And same thing I can actually copy. But here I don't have to create a new node. I just have to return the current node. So I will say if value is greater than current node dot value, then if value is large, then what do? You will search in the right node, self dot. And if there is you can either return current node or you can return if the current node is none, then return empty. If this is none, then you can return either the current node or an empty. Okay. But what I'm doing here is I'm trying to return the nearest node, basically. And I can return here none also, just to say that it is not found. And if my value is less than the current node dot value, then I will search in the left subtree. And if the left subtree is none, then I will just return none. Right. And if I find it, then I will return the value or current node, basically. Then I will return the current node. Now let's see. Bst dot search. Let's search 5. What did okay? I not executed this one. Oh, achha, I didn't print anything. Print. Okay. None. That's strange. If my value is larger than the current node, then I will search in the right current node. And if the right one is not there, then return none. And if my value is same as the current node dot value, then I will return the current node. Should work. I don't know why is it not working. Bst dot search. Okay, search value, comma, current node. If my value is large, then go to the right subtree. And if the right subtree is not there, then return none. If the value is less than the current node, then go to the left subtree. And the left subtree is none, then return none. And if the value is equal to current node value, then return. Let me say, okay. See, now I have to debug the program. I don't know how to debug. Let's see. Print. For debugging, print is the best. Is your best friend. It can help you to debug the code. Case 2. And this is case 1, case 1, case 3. It's finding the case 3. It is finding the case 3. Oh. Oh, see, I have put a blocker unnecessarily. I have to return this value, right? It should have worked. Case 1, case 1, case 3 returns value, and this returns the same value. Oh, see, this is not returning anything. Okay, now it's correct. Now it's returning it. Now, I may also return, let's say, if I search for something, let's say 7, which is not there, but I may also return the closest node, which is 6, for example. So how will I do that? I will say, instead of returning the values, I will be returning the current node. Basically, it returns the closest node. See, it returns 6. And I can finally check here that I will say here node equal to this. If node dot value is same as node dot, sorry, same as value, then you say, if it is not same as the value, then you say print not found and still return the node. Oh, it's not. Oh, is this syntax not valid? Okay, now it says not found, and then it returns the closest node. Right. Okay, so that was the search function, and let's go to theory now. So basically, I wanted to introduce you to this class, and also I want to introduce you with this node from binary tree package, which has this pretty print thing. Okay, let me change back to our OneNote. Search is done. Now let's come to the another operation which is very useful for binary trees, which is called removing or deleting some node. Delete. So let's start with some example. 5. Let's say I say remove. Let's say I say remove the node 2. How will you remove 2?
Go to the node.
Just a moment. Let's say remove 1. How do you remove 1? So you will start from the root, right? You will compare this 1 with this. Basically, you have to search for it, right? You have to search for it, and then you have to reach there. Then you have to remove that. So let's say you want to remove 1. So you will first search for 1 and then remove this node. You search for it, you found this one, then you remove this node. Basically, the parent dot left will become none, and this node gets removed, right? So this is very simple. You remove 1, just remove it. Now, but if I ask you to remove 2, how will you remove 2 now? You can't simply delete it because all the subsequent units will also get deleted then. So rather what you will do here in this case is you will remove this, means you will connect this one here and you remove this one. And similarly, when you say remove 8, something similar will happen, right? Now what happens in case of remove 8 is that this one goes away, and then whatever is here, it will come here. And it can be a bigger tree also, no problem. But everything will move here. Let's say this is 9, 12. So everything will move there. But let's say you want to remove 7. How will you remove 7? Because removing 7 means either this can come here or this can come here. So which one will come? So the answer is
Right one.
Yeah, the answer is anyone can come in principle, right? Anyone can come. But okay. Anyone can come. So if I want to remove 7, either I bring 6 or I bring 8, it doesn't matter. But I want to give you a good example here. Okay. Okay, so if to remove 7, either this or this, anyone, this or this, anyone will work. Now, what if you want to remove 10? This is a difficult case. No, this is also a simple case. Let me make it more difficult. Sorry, I'm introducing some fractional numbers now. Okay, now how do you remove 10? How do you remove 10? If you remove 10, which one will you bring? If you bring this one, then this 9.5 will clash with 12. And this one cannot have, this already has 2 children, it cannot have 3 children, right? So this is a difficult case. Difficult means it's a slightly tricky. It's not difficult, it's slightly tricky. So what you will do in this case is,
So we can link one of the child to that 10, note 10.
Which child? If I link 9, then this will have 3 children. If I link 12, it will have.
No, child of 9 or child of 12.
Yeah, how much you can go? Let's say it has more children. It has more children. Right?
Okay.
Let's say I want to remove 5 only. Then how will you do? Everybody has got so many children.
Mhm.
Right? Remove 5 will be actually good example. So which one will you bring? It has a long tree. So what you do here is, now go back to the basics, that you have to maintain the Bst invariant. So what will you do? If you want to remove, let's say 10, go to any of the subtrees, either left subtree or right subtree, and then you, let's say you go to the left subtree. Find the largest value in the left subtree. The largest value in the left subtree will be, let's say this is 9.7. And this is 9.3 something. The largest value in the left subtree is this value. Right? So you bring this one here. 10 goes away, but this 9.7 comes here. Or else you go to the right subtree and find the smallest value in the left subtree, which means you go to the right subtree and then left, the leftmost one, which is 11 here, it can come here. So this or this, any one of them will work. Right? So this is the tricky case. Okay, let me now write down the cases here. So the case 1 is that this is it's a leaf node. Leaf node means it has no children. You can simply delete it. Doesn't matter, right? Now, if you want to remove 2 or 8, it has in case of 2 or 8, they have only one subtree. Left or right, anyone. It has got only one subtree. This is case 1. This is case 2. And then in this case, 7, 10, and 5, they have all got 7, 10, and 5. They have all got both the subtrees present. This is case 4 or case 3. Both subtrees exist, or both subtrees not present. So in this case, what you will do, you will either go to the left subtree, find the largest value and put it here, or go to the right subtree, find the smallest value and put it here. Oh, if you bring this 8 here, that may be a problem, no?
Yes, sir.
Yeah, if you bring 8 here, that will be a problem. So don't bring 8. Don't bring it. So this is also the same case, basically, that you either bring the largest value of left subtree or the smallest value of the right subtree. So go to this. No, it has got no left subchild. So it's maintained. The Bst invariant is maintained. Okay, that was correct. Because I have to go to the left child of 8, which is none. So it works. Basically 8 can come here. Yeah, it's maintained, the Bst invariant. Okay, so you go to the right subtree and the leftmost child, which basically means the smallest value, or the left subtree and the largest value. So that's the algorithm. Now to implement the algorithm, you can do it in Python. It's very similar. We have already written the codes for search and insertion. Removal is also very similar. Okay. Anybody has any questions? We can stop here if no questions.
Sir, I cannot see the assignment on Mookit.
Okay, let me check. I had uploaded today. I don't know if I have to do something. Oh, publish. Okay, let me do assessment. Okay, publish. Now you can see it.
Sir, are you uploading these lectures anywhere?
Yeah, they are available on YouTube.
Sir, today I visited the YouTube page, but I didn't find. Only one lecture was there,
Oh,
first one.
okay, I'll create a playlist and share it with you.
Okay, thank you, sir.
Okay.